Ask an astronomer for the age of the universe, and you will get two conflicting answers. Depending on the method used, the universe is either 13.8 billion years old, or it is only 12.6. We have already found stars that are 13 billion years old. If that second calculation is right, these stars existed before the universe itself. It's a physical impossibility, a son born before his father. This problem is known as the Hubble tension. Imagine measuring a room with two accurate tape measures, yet they yield different lengths. In cosmology, these represent space's expansion rate. One method clocks 73 kilometers per second per milliparsec, while the other is 67.4. A 6-kilometer difference seems small, but over cosmic distances, it creates a massive margin of error. It means we are missing a distance equal to the entire width of the Earth every single second, clouding our understanding of the universe's size, age, and ultimate fate.
To find the first number, we have to go back to 1923. Edwin Hubble, working at the massive Hooker telescope, discovered that the fuzzy clouds in the sky were actually distant galaxies, and they were all rushing away from us. To measure that movement, astronomers use standard candles. Certain stars, like Cepheids, pulse with a very specific, predictable brightness. By comparing how bright they actually are to how dim they look from Earth, we determine their exact distance. This creates a distance ladder. Scientists use nearby stars to calibrate the next step out, building a chain of measurements into the deep cosmos. When the Hubble Space Telescope utilized this ladder to measure hundreds of galaxies, it calculated the expansion rate at approximately 73. Because this number is derived from the physical observation of modern stars, it serves as a concrete benchmark for our measurements of the expanding universe. The second number comes from a completely different direction. Instead of looking at individual stars, scientists look at the heat left over from the birth of the universe. This is the cosmic microwave background, the baby photo of the universe. It is fossil radiation released just 380,000 years after the Big Bang, representing the oldest light we can possibly see. When the Planck satellite mapped this ancient light and applied our standard laws of physics, the math predicted a much slower expansion rate. It came out to 67.4. Scientists now hold two flawless, thoroughly checked answers from two different eras of time. The modern universe says 73, the early universe says 67.4. At first, researchers assumed the first ruler was simply broken. They theorized that cosmic dust might be dimming the stars, tricking astronomers into seeing a faster expansion than what was actually happening. The James Webb Space Telescope was sent to test this. Its advanced infrared sensors can peer directly through cosmic dust, seeing the stars with more clarity than ever before. Nobel laureate Adam Rees and his team used JWST to recheck the original data. Their conclusion was definitive. The Hubble telescope's measurements were perfectly accurate. Observational error is now off the table. With both tape measures proven accurate, we are left with a universe that refuses to follow our established rules. Physicists have tried to fix the math with exotic theories, like temporary bursts of early dark energy or decaying dark matter. Some have even questioned Einstein's theory of gravity, though it has passed every other test we've thrown at it. This has led to a radical possibility. What if both numbers are right, because the universe is not the same everywhere? This is the local void hypothesis. It suggests that our entire galactic neighborhood is sitting inside a massive, empty pocket of space that contains far less matter than the rest of the cosmos. In this empty pocket, there is less gravity to slow things down. This would cause our local space to stretch outward faster, at 73, while the denser, distant universe follows the universal average of 67.4. Some scientists speculate this void is a buffer zone, the area where two entirely separate colliding universes are pulling away from each other. If this is true, the Hubble tension is the first evidence that our reality is just the leftover debris caught in a cosmic tug-of-war between two massive systems. The hunt for a tiebreaker is already underway. Upcoming missions like the Roman Space Telescope and the Euclid satellite will map the cosmos with unprecedented detail. By tracking dark matter and listening to the ripples from neutron-star collisions, these machines will measure cosmic distance in entirely new, independent ways. The Hubble tension marks the boundary of our current knowledge. It is the doorway to a new era of physics, one that may finally explain how our universe